Good morning, students. So we have started with the branching process. So these find applications in, for example, the survival of family names and electron multipliers, etc. So let me continue. Okay, I think my screen is now visible. So as last time we have seen, in a branching process, each individual by the end of its lifetime produce j new offspring with probability pj independently of number produced by other individual. So x naught is the size of zero generation, x1 is the all offsprings of zero generation, which is called the first generation, and xn is the nth generation. Then clearly xn size of nth generation can be 0, 1, 2, 3 and so on. So these form the state space. Clearly xn is a discrete time Markov chain because the size of xn depends on xn minus 1, not on previous uh, generations. Okay, so clearly 0 is a recurrent state, and if we have finite state, then other states will be transient. So we can make a conclusion from here that population will either die out or its size converge to infinity. So we may be interested in finding out when what is the mean of xn, variance of xn, and what is the probability of extinction. Okay, and what is the probability that size will converge to infinity, and these kind of probabilities we are interested in. So let mean number of offspring of single individual is mu, which is summation j pj, and variance is variance of single individual is denoted by sigma square. So let we are denoting the ith individual offsprings of ith individual by zi. Okay, so clearly expected value of zi is mu, and variance of zi is sigma square. So if we take x naught is equal to 1, that means in the starting one member is there, and then xn, the size of in general also xn is basically the size of the nth generation. So because xn minus 1 is the size of the n minus first generation. So z1 is the number of members produced by the first individual of the n minus first generation. Z2 is the number of individual produced by the second member of the second individual, number of offspring produced by second individual of the n minus first generation. Similarly, zxn minus 1 is the number of offspring produced by the n minus xn minus 1 nth individual of n minus first generation. So clearly xn is summation of this. Now application, as I told you that applications are in electron multiplier. So we have a source, some electrons are coming, they are hitting a plate, then some electrons are produced by the plate. So again these again strike to the plate, another plate. So again they produced. So this generates a random number of electrons. Okay, so therefore x naught is the number of electron initially emitted, x1 is the number of electrons produced by the first plate, xn is the number of electrons emitted by the nth plate. So xn constitute a Bragson So xn is basically number of electron emitted from nth plate. So due to electron emitted from n minus first plate. So xn clearly is a branching process. Second, we can take neutron chain reaction. So we have a neutron. Okay, so this collides with the nucleus. So due to fission, some more neutrons are produced, and they random number of neutrons are produced. Okay, these are random in number. That is also random in number. Okay, not that. Okay, similarly like that. Okay, so random number of neutrons are produced. So similarly, they again strike with the nucleus. So we can again form a branching process there. Similarly, third application lies in the survival of family name. So we may be interested in whether how many sons or daughters are how many children are there for a person. Okay, then similarly, first generation produced, second generation produced. So we may investigate random number of descendant of nth generation, or probability that family name will eventually be extinct. So that probabilities we can find out. So xn is basically this value, summation zi. Okay, so now we may be interested in finding out, for example, expected value of xn. Okay, that means expected number of persons in the nth generation. So we know that expected value of xn is expected value of xn given xn minus 1. Okay. Now therefore this is expected value of summation I is from 1 to xn minus 1 zi given xn minus 1, because we know that xn is summation zi I is from 1 to xn minus 1. Now we know that this value we have to calculate. So we can easily see that expected value of summation I is from 1 to xn minus 1 zi given xn minus 1 is equal to x. So because z1, z2, zn are independent individuals. Okay, so here, because this will be summation I is from 1 to x zi. Okay, so expectation, because xn minus 1 is small x, now expectation will go inside expected value of zi. This value is mu, so x mu, small x mu. So therefore this small x is replaced by xn minus 1 mu. So this will be expected value of xn minus 1 mu. So therefore this value is mu expected value of xn minus 1. Okay, so therefore since expected value of x naught is 1, so now what will be expected value of x1? Because n we can take as 1. So we will get mu expected value of x naught, that is 1. Similarly, expected value of x2 is mu times expected value of x1, mu square. Similarly, expected value of xn is mu raised to power n. So this is the value for expected value of xn is mu raised to power n, where expected value of x naught is 1 we are taking. In the starting, we are starting with x naught is equal to 1. Okay, so any question till now? Am I audible?
Yes, sir.
Yes, sir.
Okay. Okay. So now let us find out what is variance of xn. So we know that formula we have already done in probability and statistics, that just the previous classes we have done that. This is expected value of variance of xn given xn minus 1 plus variance of expected value of xn given xn minus 1. Okay. Now this quantity, inside quantity, we know that is just now we have calculated basically this value, which is same as that of this value. So this is xn mu times xn minus 1. Similarly, variance of xn given xn minus 1. So this will be, what is the variance of summation I is from 1 to xn minus 1 zi given xn minus 1 is equal to x, because xn is this value summation zi. So now again this is variance of summation i's from 1 to small x zi, but we know that zi's are independent. So this will be summation i's from 1 to x, variance of zi, but variance of zi is sigma square. So this is x times sigma square. Okay, so this is the value. Now, therefore, this value, inside value, is we are replace, because here small x is there. So we have to replace that by capital Xn minus 1. So therefore, we have sigma square x n minus 1. So therefore, this will be sigma square expected value of xn minus 1 plus mu times mu square times, because variance of mu xn minus 1. So mu square times variance of xn minus 1. Okay. So therefore this value is sigma square, but we know that xn minus 1 will be mu n minus 1 from here. Plus mu square variance of xn minus 1. So therefore this value is sigma square mu n minus 1 plus mu square. Now variance of xn minus 1, again from this use iteratively this value. So this will be sigma square mu n minus 2 plus mu square variance of xn minus 2, recursively using this. Okay, that means use iteratively this value we are using. So we can write down this star using star. Okay. Now Therefore, this value is sigma square mu raised to power n minus 1 plus from here mu raised to power n plus mu raised to power 4 variance of xn minus 2. Again, recursively using, we will get sigma square mu n minus 1 plus mu n plus mu 4 sigma square mu raised to power n minus 3 plus mu square variance of xn minus 3. So therefore, this will be sigma square mu n minus 1 plus mu n plus mu n plus 1 from here plus mu 6 this value variance of xn minus 3. So this value we are getting. Now again recursively using these values, we will get sigma square mu raised to power n minus 1 plus mu n plus mu raised to power this mu raised to power variance. In the last we have variance of x0. So this will be 2n and this value will be 2n minus 2. Okay, so this value we are getting in the last after solving this. Now this is equal to sigma square mu raised to power n minus 1 1 plus mu raised to power n minus 1. Now variance of x naught, can anyone tell? X naught is 1. What is variance of x naught? X naught is 1 here.
0.
0, yes. So variance of x naught is 0. So this is the value we have. So therefore, variance of xn, if mu is not equal to 1, this is sigma square mu raised to power n minus 1 1 minus mu n upon 1 1 minus mu. If mu is equal to 1, this value will be 1. This is 1 plus 1 plus 1. So this is basically n values, n sigma square okay. So this is the variance of x naught. So now other thing we may be interested in branching process, maybe what is the probability that population will die out in nth step. Okay, that means sorry, population will be nth generation population will becomes extinct. Okay, so we may be interested in, let us say, un plus 1, which is the probability that x n plus 1 is equal to 0. That means n plus 1th generation, the population becomes extinct. So this using the theorem of total probability, this is probability x n plus 1 is equal to 0 given x1 is equal to j into probability of x1 is equal to j, that is pj. So therefore this is starting with, because each individual is independent. So we are saying that starting with j individual, in nth step the population becomes extinct. So summation j probability xn is equal to 0 raised to power j pj. Okay, so this is the value, because there are j members independently, they are producing offsprings, and in according to this, in if they are starting j members, in nth step the population become extinct. That means each individual member becomes 0. That means probability xn is equal to 0 raised to power j in the branching process. So therefore this is summation j. We are denoting this by un raised to power j pj. So that is the recursive, that is the basically equation. Iteratively we can, so because basically we can solve this. So therefore un, or we can write down un plus 1 is equal to summation j unj pj. So we can solve this and find out the answers. Now another thing which may be interested in, the that population become extinct. What is the probability that ultimate extinction probability, because this is the probability of extinction in n plus 1th, for n plus 1th generation. But what is the probability of ultimate extinction? That probability that population eventually die out under the assumption that x naught is 1. So we may be interested in probability of ultimate extinction. That means let pi naught is the probability that population will eventually die out. So we are taking the assumption that under the assumption that we are starting with one member. So that is the probability of ultimate extinction. So pi naught is limit as n goes to infinity, probability xn is equal to 0 given that we start with one member. So our claim is that first of all, note down that pi naught pi naught is equal to 1 if mu is less than 1. What is mu? Mu is basically mean of xn. Okay. Expected value of x1 basically. Okay, so x1 is mu basically. That means mu is basically the mean number of offspring of single individual. That is mu. Summation j pj. Summation j pj basically that is mu. So let us say what is mu n. Just now we have shown that mu n is expected value of xn. That is summation j probability xn is equal to j. Now therefore this quantity is greater than equal to summation j 1 times probability xn is equal to j. Now this is probability xn now j is basically 1 to infinity, because here j is from 1 to infinity, because 0 will be there, then this will be 0. Okay, so because 0 we will take, but that doesn't matter because it will start from 1 basically. So therefore this is probability xn is greater than equal to 1. Now since mu is less than 1, so therefore mu n goes to 0 if mu is less than 1 as n goes to infinity, as n is large. So therefore this value probability greater than 1. Now this side goes to 0. Therefore this quantity also goes to 0. So therefore that is probability xn is equal to 0 goes to 1. That is pi naught is equal to 1. So therefore we have shown that if your mu is less than 1, then pi naught is 1. Then probability of ultimate extinction is 1. That means in the last population will die out. That is the conclusion. Now it can be shown that pi naught is equal to 1 even when mu is equal to 1. When mu is greater than 1, it turns out that pi naught is less than 1. But how to calculate that? Then pi naught is basically probability that population dies out. So this is summation j probability that population die out, given that x1 is equal to j into pj. So starting with j members, starting with let us say one member, population die out. That is pi naught. Okay, taking limit also. So therefore because each individual is independent in the branching process. So starting with j members, population die out is pi naught raised to power j. Pj. So therefore, we have to solve this equation. Pi naught is equal to summation pi naught raised to power j pj to find out the answer basically for pi naught in when mu is greater than 1. So it can be shown that when, because this is, so pi naught is the smallest positive number satisfying equation okay. So this equation which satisfies, so any question till now? Yes, any question? Okay, let us take an example. So am I audible now?
Yes, sir.
Okay. Okay, so let us say that we are starting with the one individual and individuals are independently producing offspring such that zero individual, a member will produce zero individual probability half, one member with probability 1/4, and it produces two offsprings with probability 1/4. Determine pi naught that population will eventually die out. So first of all, we have to calculate mu. So mu is 0 into half plus 1 into 1/4 plus 2 into 1/4, 3/4. So this is less than equal to 1. Because this is less than equal to 1, so therefore clearly our pi naught is 1 due to the previous discussion. So therefore pi naught is 1. So therefore population will eventually die out. That is the conclusion. Now let us say that we are starting with one individual and P naught, that means a member number of offspring produced by a single individual is 0 with probability 1/4. It produces 1 with probability 1/4. Two members offspring it produce with probability 1/2. So what is pi naught? Probability of ultimate extinction. So we know that first of all we have to calculate mu. So 0 into 1 by 4, 1 into 1 by 4, 2 into 1 by 2. So therefore this is 5 by 4. This is greater than 1. So therefore we know that solution pi naught is given by pi naught is equal to summation j pi naught raised to power j pj star, okay, using star. So that means pi naught is equal to p naught. P naught is 1 by 4 plus, when j is 1, this is pi naught p1 1 by 4 plus pi naught square p2. P2 is half. So therefore this is multiply with 4. Okay, so this is 2 pi naught square. Okay, then minus 3 pi naught plus 1 is equal to 0. So can anyone provide the answer? What is the value of pi naught? Yes, answer is, what is the answer?
One and a half.
Yes. So 1 comma half, but we know that the smallest positive number satisfying this equation is the answer. So therefore this is the answer. Pi naught is equal to half. That means probability that population will eventually die out is half. That means probability of ultimate extinction is half. So that is the answer basically for this question. Now let us say in these questions, the let us say we start with n members. So now, so for the first part, if we, because in the first part we have started with one member, second also we started with one member, but we know that individuals are independent. So therefore, if we take the first part, only difference is that x naught is n instead of 1. Then answer will be pi naught raised to power n. So answer will be pi naught raised to power n. Population will die out. Okay, so that is the probability of ultimate extinction. Okay, so this is the probability. So in the first part, this becomes pi naught raised to power n, which is 1. Second part, it becomes pi naught raised to power n, that is half raised to power n. So that is the answer. Yes, any question till now? So this completes branching process. Any question in the branching process? Okay, then, so let me just start with the, now we have already started with the Poisson process. Because in the introduction to probability, we have done the Poisson process. Okay, so let me just, so yes, any question? Not audible, so can you just, some question is there, can you just ask? Okay, so Poisson process, so events are occurring in time, NT counts the number of events occurring in the interval 0 to t. NT is said to follow Poisson process if NT has independent and stationary increment in a very small interval, either 0 and 1 event occur. So NH is 1, lambda h plus small oh, and NH is greater than equal to 2 is small oh. Okay, so under these assumption, we have already shown that probability NT is equal to n is e raised to power minus lambda t raised to power n divided by n factorial, and one example we have discussed. Okay, now sum of independent Poisson process is a Poisson process, and we have because how we will show this thing, first one, so we can use the moment generating function approach and we can show this. And for the second part, whether we have done this second part, okay, so we have to show that suppose each time an event occurs is classified as type 1 or type 2, each event is classified as type 1 with probability p and classified as type 2 with probability q. NT and NT is a Poisson process. Then show that N1T is a Poisson process with rate lambda p, N22 is a Poisson process with rate lambda q, and N1T and N2T are independent. Okay, so we are showing this. So we have that our N1T is the number of type 1 event and N2T is the number of type 1 event. Okay, such that and is the in the event in the interval 0 to t, number of type 1 event in interval 0 to t. Okay, now NT is N1T plus N2T. Now, if NT is Poisson process with rate lambda, then show that N1T is Poisson process with rate lambda p, N2T is a Poisson process with rate lambda q, where p plus q is 1. Okay, and such that it is also known that, okay, so that means uh, p is the probability that each event is classified as basically is type I, probability of event is type I. Q is the probability that event is type 2. For example, we have given started with this here. Yes. This one, this example basically. NMT, NF, for example, number of male in a class, some students are coming, and NMT is the number of students, male student coming in the interval 0 to t, NFT is the number of female student coming in the interval 0 to t, and T is the total number of students coming in the interval 0 to t. So then each student is a male with probability q, p, and each student is a female with probability q. Then show that NMT is Poisson process with rate lambda p, NFT is a Poisson process with rate lambda q. So I am writing here C Poisson process class later for solution. Okay, so now this thing we have to show. His question is clear. What we have to show? Yes, his question is clear.
Yes, sir.
Okay, so let us take probability that, let me denote this by Ni. N1 is equal to N, N2 is equal to M. So this can be written as probability that, using theorem of total probability, this can be written as probability N1 is equal to N, N2 is equal to M, given N is equal to N plus M into probability N is equal to N plus M, but N is Poisson process. This is e raised to power minus lambda t is a Poisson process. So lambda t, so let me just write down lambda only. Okay, lambda raised to power N plus N, N plus N factorial, because t will basically in the same fashion it can be adjusted. Okay, so now, because this will be summation, N is equal to I, but N cannot take other values because N1 is N, N2 is M. So if N I take some other than N plus M, then that probability, conditional probability will be 0. So now it is saying that this out of N plus M, N are of one type, M are of other type. So this is the binomial distribution N C N, because N with probability P, the males are type 1 are N, P raised to power N, Q raised to power M, e raised to power minus lambda, lambda raised to power N plus M upon N plus M factorial. Now, this is n plus m factorial upon n factorial m factorial. Now, p raised to power n, q raised to power m, e raised to power minus lambda p, e raised to power minus lambda q, because p plus q is 1, lambda raised to power n, lambda raised to power m, because lambda raised to power n into lambda raised to power n is lambda raised to power n plus m. N plus m factorial. This will cancel out. This is e raised to power minus lambda p raised to power n upon n factorial, e raised to power minus lambda q raised to power m upon m factorial. Okay, so lambda, if you want, you can write down lambda t also in the starting. So then same t will carry out in each of them. Okay, just for convenience I am writing, otherwise you can write lambda t also, that doesn't matter here. So lambda t, okay. So therefore, what is the probability? N1 is equal to n. How to find the marginal distribution? From the joint, because this is the joint of n1 comma n2. Anyone? What is the marginal of n1? Marginal probability mass function? Sum over some joint m. You have to say that thing. Okay, so because if we have a joint distribution, then marginal is finding out summing over the other values. So if we sum over m, this quantity will be outside, summation over this value, double dot values. Okay, so therefore, because this is we can see that Poisson again, so that summation will be 0, summation will be 1. So therefore, this is e raised to power minus lambda p raised to power n upon n factorial. Okay, so here n is your 0, 1, 2 and so on. So what is the distribution of n1? Can anyone tell? Because t I have dropped. Am I audible? Am I audible?
Yes, sir.
So which distribution is this? This is, if I take lambda, because
Poisson with
lambda,
rate lambda p.
yeah, so this is Poisson process basically, because here I have dropped t notation. So therefore this is basically Poisson process with the rate lambda p. Similarly, N2T is a Poisson process with the rate lambda q, and you can see that because joint is product of their marginals, so therefore both of them are independent also. Okay, so therefore we have shown this thing. Okay, so just only think, instead of lambda t is there, so you can adjust in the same fashion the proof. So therefore this is the answer. So let us stop here. So next time we will start with this Poisson and interrelated distributions. Any question till now?